In this video, I'll explain the physics behind quantum entanglement. For more clarification, I recommend that you visit entanglementsolved.com. Equal change and equal timing are the secret behind entanglement. But, how do they work? Albert Einstein once said, and I quote, "Insanity is doing the same thing over and over again, and expecting different results." If you study this statement carefully, it means, if someone or something does the same thing repeatedly, they will always get the same results. I'm going to use your understanding of this statement to explain the physics behind entanglement. There are many assumptions that has led to different misconceptions about quantum entanglement. Before I start this video, I need to clarify at least 3 of them. 1. The mere act of looking or consciousness doesn't affect the state of a quantum object or wave. Only a measurement does. Measurement in quantum mechanics is described as any external influence that can physically interfere with a quantum object. 2. A measurement made on one entangled particle at 5:20 p.m., for example, cannot affect or collapse the quantum state of the other entangled particle at any time. It only provides knowledge of the spin orientation or quantum state of the other particle if it had been measured at 5:20 p.m. 3. The father of all misconceptions in quantum entanglement is the notion that the quantum state of one particle after it has been measured is what determined or forced the other entangled particle to choose the opposite state. The notion that one entangled particle forced the other entangled pair to choose the opposite state is an unforgivable wrong assumption that has been spread by many physicists and bloggers. In fact, what we do know is that, if we measure the quantum state of one entangled particle, let's say at 10 p.m. on the dot, and we determine the quantum state to be spin up. At the same instant, we would know if we had measured the other entangled pair at 10 p.m. on the dot, it would have the opposite state. Our measurement doesn't collapse or force the other particle to do anything wherever it is, it only gives us knowledge of the particle's quantum state at a specific time. How and why this happens is the purpose of this video. Let's use the electron as example. The electron is a very tiny particle of matter that behaves like a magnet. For this explanation, here are 2 things you need to know about the electron. The electron have a conserved angular momentum which is directly related to its spin. You can read more about spin on the website I provided in the beginning of this video. But for the sake of this video, spin is a dipole that is observed around a quantum object which constantly changes directions. Because quantum angular momentums are conserved, the spin of an electron is constant. In other words, the rate at which the spin of an electron changes direction cannot go faster or slower. Every electron in the universe spins at the same rate. If you think of the electron as a clock, the angular momentum of an electron can be compared to a clock spinning on its axis, while the spin of an electron can be compared to the clock hand. If you know one thing about a clock, you know that every clock hand ticks at the same rate or speed. But in the case of the electron, it only has one clock hand, which we refer to as dipole, or spin orientation. The spin orientation can be measured in any direction around the electron, but the final outcome of the measurement can only appear spin up, or spin down. Before I continue, let me explain the concept of equal time. Because of the magnetic nature of the electron, which only allows the spin of the electron to collapse in the north or south pole, if you decide to measure the spin orientation of an electron in the vertical axis. But, at the moment you measure it, the spin orientation is located somewhere in between up and down heading in the south pole direction, the spin will immediately collapse in the down position and vice versa. It doesn't matter where the orientation is located within the vertical length of the electron, it will always collapse in the direction that correspond to that side. In this case, right correspond to spin down, and left correspond to spin up. As a result, if I send out a single photon to measure 2 entangled electrons, if the spin orientation of electron 1 is detected by the photon on Earth at 1b, and then the photon travels to the Moon and detect the spin orientation of electron 2 at 4d, the final outcome of both electrons will be spin down. Equal time therefore means, any time within the corresponding vertical length of 2 entangled objects. With that being said, let's return to our clocks. Notice that even though these 2 clocks are separated by distance, the rate at which their hands tick are equal. And because both clock hands began to tick simultaneously, if we stop them at the same time, their changes will be equal. We can go further by increasing the speed of the clock hands. Yet, provided their speed is equal, and they begin motion at the same time, their changes will be equal if we stop them at the same time. Stop in this sense means measurement. For the next 10 seconds, pause this video at any time to simulate equal time measurement. Okay, let's move on. The behavior of quantum objects obeys certain laws. One of these laws is the Pauli exclusion principle. For the purpose of this video, I will narrow the principle down to the electron. Pauli exclusion principle as it relates to the spins of fermions, such as the electron, states that two electrons in close proximity cannot have the same spin orientation. This is similar to saying, in close proximity, two identical magnet poles will repel. Only opposite magnet pole can attract. Therefore, using the clock as analogy, when both clocks get close to each other, both clock hands will switch to opposite orientation, as seen here. The moment they separate, they will begin motion again at the same time. Because the clock hands have equal speed, and they begin motion simultaneously, for the next 10 seconds, if you pause this video at any time to simulate equal time measurement, the hands of the clocks will always be opposite. Okay. Now, let's use electrons for demonstration. Here are two non-entangled electrons. I slowed the dipole down so you can see how the spin orientation changes directions. Now, I'll allow the two electrons to get close to each other. The moment they interact via the electromagnetic force around them, their spin orientation will switch to opposite directions, as stated in the Pauli exclusion principle. This also happens when two electrons emerge from the same source. The moment both electrons separate, their spin begin motion simultaneously. This changes is so fast that the spin orientation would appear to be in two places at the same time. This state is referred to as superposition. A state where the spin orientation of the electrons doesn't have a specific direction. However, provided their equal spin speed are not interrupted by external forces, regardless of the distance between the two electrons, their changes will always be opposite if measured at the same time. For the next 2 minutes, pause this video at any time to simulate equal time measurement. Pausing this video at any time allows you to see the results of two entangled particles when they are measured at the same time. With this knowledge, assuming you have one entangled electron in your bedroom, and the other entangled pair is located somewhere on the moon. If you want to know what the spin orientation of the electron on the moon would be at exactly 3:16 p.m., all you need to do is measure your electron at exactly 3:16 p.m. If your electron is spin up at 3:16 p.m., then you can say, at exactly 3:16 p.m., the spin orientation of the electron on the moon was spin down.